Hello learners, today we are going to derive the Laplace transform of a function f of t is equals to sin lambda t. We know that Laplace transform transforms a function f of t into a completely different function capital F of s, which is given by integration from infinity to 0 exponential minus st f of t with respect to t. Our f of t is sin lambda t. So we are looking for the Laplace transform of sin lambda t, which will be transformed to a completely different function capital F of s, which is given by the integral from infinity to 0 exponential minus st f of t with respect to t. Now, our f of t here is sin lambda t. Our f of t is sin lambda t. So this is sin lambda t with respect to t. Now we are going to integrate this function using integration by parts. We are going to integrate it by integration by parts. i.e., integration by parts tells us that the integral of u dv is given by uv minus the integral of v du. With this, we are going to let sin lambda t to be our u, and we let exponential minus st dt be our dv. So we are saying that let u be equal to sin lambda t. If we differentiate u with respect to t, we are going to get du dt to be equal to lambda cosine of lambda t. If we multiply both sides by dt, we are going to get du to be equal to lambda cosine of lambda t dt. Now we have our u, we have our du. Secondly, we are saying that we are going to let dv be equal to exponential minus st dt. If we neglect dv, we get v. If we neglect exponential minus st with respect to t, we get minus 1 over s exponential minus st. Now we have our dv and we also have our v. Let's now replace. We are going to replace to find that the Laplace transform of sin lambda t is being given by our integration here is u. Our u is sin lambda t. Our v is minus 1 over s exponential minus st. This is from infinity to 0. Minus the integral from infinity to 0. V, our v is minus 1 over s exponential minus st. Our du is lambda cosine of lambda t dt. Now, that is a Laplace transform sin lambda t. Let's now replace the boundaries. We are going to get the Laplace transform of sin lambda t will be equal to, where there is t, we replace with infinity for the upper boundary. Sin t being infinity times anything, you get infinity minus 1 over s exponential minus t is infinity times anything, you get infinity, so you are going to get exponential minus infinity minus the lower boundary is t being 0 times anything, you get 0, sin 0 into exponential minus st, t being 0, t times anything, you get 0. It will be minus 1 over s exponential 0 minus the second part of the equation from infinity, integration from infinity to 0 minus. There is this minus and this minus. This minus, everything is being multiplied. So this minus and a minus, they become a plus. Remember, a minus times a minus, you get a plus. So this minus and this becomes plus. There is also lambda and 1 over s. Lambda times 1 over s, these are constants. We multiply them. Constants are always outside the integration sign. So lambda times 1 over s, we get lambda over s as our constants, which are taken outside the integration sign. So we remain with exponential minus st cos lambda t with respect to t. Now, let's now start replacing. Exponential minus infinity is 0. Exponential minus infinity is 0. When you multiply 0 with anything, you get 0. So the whole of this is 0. Sine 0 is 0. Sine 0 being 0, when you multiply it with anything, 0 times anything, you get 0. The whole of this is 0. So we are left with, we are going to be left with Laplace transform of sine lambda t, this being equal, this is 0, this is 0, being equal to lambda over s here, integration from infinity to 0 here, exponential minus st cosine of lambda t with respect to t. Again, we are going to integrate this by integration by parts. Again, we are going to integrate again this by integration by parts, where we are going to say the integral of u dv is equals to uv minus the integral of v du. This is integration by parts formula. Now, we are going to let u to be equal to cos lambda t. If we differentiate u with respect to t, we have let this to be our u, and we are letting this to be our dv. Cos lambda t is our u, exponential minus st dt is our dv. So we have let u to be equal to cos lambda t. If you differentiate u with respect to t, we are going to get du dt is to be equal to minus lambda. When you differentiate our cosine, you get minus lambda sine lambda t. If we multiply both sides by dt, we are going to get du to be equal to minus lambda sine lambda t dt. We have our u again, we have our du. We have said that we are letting dv to be equal to exponential minus st dt. If you integrate dv, you get v. If you integrate exponential minus st dt, you get minus 1 over s exponential minus st. Now, let's replace with the formula. We are getting Laplace transform of sine lambda t to be equal to, there is this constant outside the bracket, this constant lambda over s. Do not forget this constant lambda over s. Laplace transform of sine lambda t is equals to this constant, and then now we are integrating this using integration by parts, which is this formula, where we are going to get u. Our u is cos lambda t into times our v is minus 1 over s exponential minus st. This is from infinity to 0 minus integral from infinity to 0. The integration of v, our v is minus 1 over s exponential minus st. Our du is minus lambda sine lambda t dt. Now, let's start putting the boundaries. We are going to get the Laplace transform of sine lambda t to be equal to lambda over s. Then, for the first, for the upper boundary, t will be replaced with infinity. So, t is infinity. Infinity times anything, you get infinity. So, it is going to be cosine of infinity into exponential minus st, and t is infinity. Infinity times anything, you get infinity. So it will be minus 1 over s exponential minus infinity. T is infinity. Infinity times anything, you get infinity. So it is exponential minus infinity. Minus the second boundary, which is the lower boundary, t is replaced with 0. Cos of lambda t, it will be cosine of t is 0. 0 times anything is 0. Into 1 over s. Exponential minus st. T is replaced with 0. 0 times anything is 0. It will be exponential 0. Minus the integral from infinity to 0. Now, here, let's look at this function. Everything is being multiplied. We have a minus and a minus. We have said that a minus times a minus, you get a positive. So this minus and this will be multiplied to become a positive. And then we have our third minus here. So this, our third minus, will remain here. And these two will multiply to become a positive. How many constants do we have? We have a constant lambda, and we have a constant 1 over s. Lambda times 1 over s, we get lambda over s. We get lambda over s outside our integration. This and this we have multiplied, then taken them out. This minus and this minus. Minus times minus, it becomes plus, like I have said, and this negative remains. It is this one. This lambda is this one. 1 over s is here. We are remaining with exponential minus st sine lambda t with respect to t. Now, that is what we have. Let's close the brackets. Let's now close the brackets and see what we have. Now, here, I want you to understand that exponential minus infinity is 0. Exponential negative infinity is 0. When this becomes 0 and you multiply it with anything here, everything here becomes 0. Remember, 0 times anything becomes 0. So exponential minus infinity is 0. 0 times anything, this becomes 0. Then cos 0 is 1. The cosine of 0 is 1. Again, exponential 0 is 1. Exponential 0 again is 1. So what are we going to remain with? Laplace transform of sin lambda t here to be equal to lambda over s. Here, this, the whole of this is 0. The whole of this becomes 0 because of exponential minus infinity. So we have that 0. Then the cosine of 0 we have said is, there's this minus here, this minus and this minus. These two minuses, let's first remain with our minus, like we see. Minus cos 0 is 1, there is a 1 which is for cos 0. Then into brackets, minus 1 over s. This is minus 1 over s. Then exponential 0 again is 1. Now we have replaced everything here. Cos 0 is 1, minus 1 over s there, and exponential 0 is this 1. Now, minus here, lambda over s, integral from infinity to 0, exponential minus st, this one, sine lambda t with respect to t. That is what we have. Let's close our brackets. Here, we get Laplace transform of sin lambda t to be equal to lambda over s into, this is 0. 0 minus, remember 1 times anything, it is that thing. When you multiply 0 and with any number, you get just that number. So this 1 and 1, if you multiply them, remains 1. You have 0 minus 1 over s. 0 minus 1 over s. Minus and a minus, it becomes a plus. When there's two minuses from each other, it becomes a plus. So you have 0 plus 1 over s. 0 plus 1 over s is just 1 over s. 0 plus 1 over s is just 1 over s. You have 0 minus 1 over s. this minus and a minus, they become a plus, then 0 plus 1 over s is just 1 over s minus lambda over s. Integral from infinity to 0, exponential minus st sine lambda t with respect to t. What do you notice with this function here? This defines the Laplace transform of sine lambda t. The Laplace transform of sine lambda t is what is given by the integral from infinity to 0 exponential minus st sine lambda t dt. So this in the rectangle, when circled in a rectangle, represents or defines Laplace transform of sine lambda t. So this bracket is closed. We are going to remain with Laplace transform of sine lambda t being equal to lambda over s, this one, into, we have 1 over s minus, we have this lambda over s into. This defines Laplace transform of sine lambda, like I have said, Laplace transform of sine lambda t. So after getting that, we have remained with this. We have said that exponential from infinity to 0 exponential, integral from infinity to 0 exponential minus st sine lambda t dt defines Laplace transform of sine lambda t. I want you to understand that. Now, let's start multiplying, opening the bracket, where we are going to multiply everything by lambda over s. We are going to get Laplace transform of sine lambda t being equal to lambda times 1, lambda, all over s times s squared, minus lambda times lambda, lambda squared, s times s squared, into Laplace transform of sine lambda t. That is what we are remaining with. So, when we remain with this, let's take Laplace transform, let's take the whole of this term to the other side. We are going to get Laplace transform of sine lambda t. This we are going to take it to the other side. Minus becomes a plus. We are taking it to this side. So this minus will become a plus. So we are going to plus lambda squared over s squared, Laplace transform of sine lambda t is to be equal to lambda over s squared. We have taken this to the other side so that it becomes Laplace transform of sine lambda t plus, now this lambda squared over s squared, Laplace transform of sine lambda t to be equal to this here, you can see. Now let's factor out Laplace transform of sine lambda t. Let's factor out Laplace transform of sine lambda t. Laplace transform of sine lambda t, when you factor it out, this you remain with 1. So that Laplace transform of sine lambda t times 1, you get this plus. Here you are going to remain with lambda squared over s squared so that when you multiply this and this, you just get this term to be equal to lambda all over s squared. Now let's divide both sides by 1 plus lambda squared over s squared. We are going to divide here, divide by 1 plus lambda squared over s squared, and divide here by 1 plus lambda squared over s squared. This goes with this. We remain with Laplace transform of sine lambda t to be equal to lambda over s squared all over 1 plus lambda squared over s squared. We can choose to work with the denominator first. Let's work with the denominator first. We can write it as 1 is same as 1 over 1 plus lambda squared over s squared. We are working on this first. Let's add it. When we add, we take the LCM. Let's take our LCM here is s squared. S squared divided by 1 is S squared times 1, it is S squared. S squared divided by S squared, you get 1. 1 times lambda, you get lambda squared. So this can be written as this. This term can be worked out to be this term here. So we can just come here and write this as equal as lambda over S squared all over. Remember, we have worked on this to get S squared plus lambda squared all over S squared. Now, that is what we are going to get right now. After getting this, we have seen that we will have our Laplace transform of sin lambda t to be equal to lambda over S squared. This over this can be written as just divided by S squared plus lambda squared all over S squared. Can be written over means just divided by, where we are going to get our Laplace transform of sin lambda t being equal to, when we divide, we multiply and invert our term lambda over S squared times S squared all over. We are inverting this term so that this division changes to multiplication all over S squared plus lambda squared. S squared goes with S squared. We remain with Laplace transform of sin lambda t being equal to S squared goes with S squared. We remain with lambda all over S squared plus lambda squared. And learners, the Laplace transform of sin lambda t is given by this, by lambda all over S squared plus lambda squared. That is how we derive Laplace transform of a function f of t is equals to sin lambda t. In the next lecture, we are going to derive the Laplace transform of a function f of t is equals to cos lambda t. Thank you. Have a good day.